welcome to another WJEC A-Level Physics question. This time is question 2 from June 2008's PH5 paper, and it's on nuclear decay, nuclear energy, and that nowadays is found in Unit 3. So the question starts off by talking about a possible reaction for future fusion power stations on Earth is the fusion of deuterium with tritium, and then we've got an equation given for it. We've got to determine a mass number and atomic number of X and state its name. Well, remember that the mass numbers and the atomic numbers are basically equations here. So looking at mass numbers, we've got 2 plus 3 on the left, we've got 4 on the right, so there must be a 1 for the mass number for X. Similarly on the bottom, we've got 1 and 1 on the left, 2 on the right, so the numbers are already balanced, so the atomic number must be 0. So let's write them down just for clarity. So the mass number is 1, atomic number is 0. So our particle is a particle that's in the nucleus. It is a nucleon, but it's not a proton, so X is a neutron. Next, we're given the nuclear masses and we've got to calculate the energy released in the reaction. So this is just a standard question. We find the total mass on the left, the total mass on the right, and subtract them and then turn that into energy. So the total mass on the left is going to be 2.0136 plus 3.0155. And we're going to subtract the total mass on the right, 4.0015 plus the 1.0087. Now normally I would do this in one calculation, but let's do it in steps just to prove that there is more mass on the left than on the right. So on the left we have 5.0291, on the right we have 5.0102. So we can see that there is more mass on the left than the right. The difference is 0.0189. And to turn that into energy, we simply multiply that by the 931 MeVs that were given in the question. And that will give us about 17.6 EVs. Next we've got to calculate the energy released in joules when 1 mole of the the deuterium fuses with 1 mole of the tritium. So first of all, let's turn that energy into joules. So we've got 17.6 is mega electron volts. And to turn electron volts into joules, we multiply by 1.6 times 10 to the minus 19. And that will give us 2.8 times 10 to the minus 12 joules. Now, the energy that we've calculated, that's the energy released when 1 deuterium nucleus fuses with 1 tritium nucleus. So all we're going to need to do to find the total energy is multiply that answer by the number of nuclei in a mole, which is Avogadro's number, 6.02 times 10 to the 23. And if we do that, we end up with 1.69 times 10 to the 12. And finally, we're going to explain briefly how we know that the nuclear binding energy of the helium is greater than that of the deuterium and tritium combined. Well, we've already shown that the mass on the right hand side is less than the mass on the left. So energy is released, or if you like, more binding energy must be on the right hand side. And another important point here is that the neutron doesn't have any binding energy because it isn't bound to anything. So clearly then it should be obvious that all of the binding energy on the right belongs to the helium, and that's going to be more than what we had on the left hand side. Thank you for listening. Please remember to like and subscribe, and feel free to leave any questions. Goodbye.